Hey everyone, I am Miss Hu, your physics teacher. In this video, I'm going to go through an overview of the magnetism segment of Unit 4 in the IGCSE Physics 0625 2023 to 2025 syllabus. Now, this is not a complete unit. Unit 4 is actually electricity and magnetism, but because the unit is really long, I've decided to divide the overview videos into two. So one video on magnetism and one video on electricity. So if you're looking for the revision on the electricity segment, please watch that video instead. So this video is meant to be an overview video, so it's merely a refresher and revision video for those who have already learned this unit. If you're learning these topics for the first time, or if you need revision on specific topics in this unit, please watch my videos on those specific topics instead. Because this is meant to help students prepare for their examinations, in this video there will be a lot of references to the syllabus guide, just to make sure we've covered everything that we need to know to prepare you for your exams. So let's get started. So the first thing you need to know is about magnetism. You need to be able to describe the forces between the magnetic poles and between magnets and magnetic materials, including the use of the terms North Pole, South Pole, attraction and repulsion, as well as magnetized and unmagnetized. You need to be able to explain the magnetic forces are due to interactions between magnetic fields, describe induced magnetism, state the differences between the properties of temporary magnets which are made of soft iron. I'm just going to highlight that real quick because you are expected to know that soft iron is used as temporary magnets, and the properties of permanent magnets which are usually made of steel. You need to be able to state the difference between magnetic and non-magnetic materials, describe a magnetic field as a region in which a magnetic pole experiences a force, draw the pattern and direction of a magnetic field lines around a bar magnet, just like the one in this diagram here. You must remember that the magnetic fields go from north to south, outwards from north, inwards to south. You need to know that the relative strength of a magnetic field is represented by the spacing of the magnetic field lines. So the closer the magnetic field lines are to each other, the stronger the magnetic field strength. You need to be able to state that the direction of a magnetic field at a point is the direction of the force on the north pole of a magnet at that point. You need to be able to describe the plotting of the magnetic field lines with a compass or iron filings and the use of a compass to determine the direction of the magnetic field, which is the experiment that you should have already learnt about using compass and the iron filings. And you need to describe the uses of permanent magnets and electromagnets. So I'm not going through all this in great detail because, like I said, this is an overview video, and all of these stuff you've actually already learned this in Key Stage 3. Depending on your school, you should have learned this either in year 7, 8 or 9. So this is pretty much basic stuff you should already know, so I'm not going to go into much detail. Let's instead move on to the next part, which is on the magnetic effect of current. You need to be able to describe the pattern and direction of the magnetic field due to currents in straight wires and solenoids. So in a straight wire, the magnetic field is around the wire, so it's circular. So if you take the wire and put it into a loop, you'll get two circular magnetic fields, and depending on the direction of the magnetic fields, you'll find that if the current is in opposite direction in the loop, because same wire, right? So that's why you find in the middle the magnetic field strength is stronger because they're all going in the same direction. And in a solenoid, which is essentially an electromagnetic coil like this, you'll get magnetic fields around the solenoid looking like this, pretty much identical to the bar magnet. Now you also need to be able to state the qualitative variation of the strength of the magnetic field around straight wires and solenoids. So this is similar to what we've seen in the previous slide, which is that the smaller the distance between the magnetic field lines, the greater its magnetic field strength. Now you also need to be able to describe an experiment to identify the pattern of the magnetic field, including direction, due to currents in straight wires and in solenoids, which is similar to what we saw in the previous slide, using a compass and iron filings. You also need to be able to describe the effect on the magnetic field around straight wires and solenoids of changing the magnitude and direction of the current. Basically, by increasing the magnitude of the current, the magnetic field strength becomes stronger, and changing the direction of the current changes the direction of the magnetic field. Now, you also need to be able to describe how the magnetic effect of a current is used in relays and loudspeakers and give examples of their applications. So what we have on the left here is an example of a circuit diagram of an electromagnetic relay. So this circuit, also known as the primary circuit, has a solenoid here. So when we close the switch, the solenoid will then become an electromagnet. This green thing is the iron armature, which would be attracted to the solenoid when it becomes an electromagnet. So this end goes down, causing the entire iron armature to rotate and pushes these two contacts together. So as you can see, currently the contacts are separated, but once the iron armature pushes the contacts together, they're actually quite flexible. They'll touch, completing the secondary circuit, which is where the motor would be. Then when we switch off the circuit, the solenoid stops becoming an electromagnet, the iron armature will rotate back into its original position, and then the contacts would separate. So this is the electromagnetic relay circuit diagram. How they normally draw the electromagnetic relay in a circuit using symbols would be like this. It's a combination of number 2 and number 3. So what I've enclosed here in this square, that's the electromagnetic relay. So the blue circuit here is the primary circuit, while the red circuit is the secondary circuit. So an electromagnetic relay is normally used to start a second circuit which has a higher voltage compared to the voltage in the primary circuit. By the way, in case you're wondering how come this red circuit is incomplete, yes, I've just noticed. I actually took this off the internet. So let's just put a power supply here, which I'll label as PS. That's your power supply. Without a power supply, obviously the device here, number 4, whatever it is not going to start. Anyway, let's move on to loudspeakers. So briefly, you need to know how loudspeakers make use of the magnetic effect of currents to work. So normally within the loudspeaker, there is a paper cone. It's usually made out of paper or some other material that's very thin and light so that it can move easily. There is a permanent magnet where there's the fixed north and south pole. And a coil here is part of an electrical circuit, which contains the current from which the sound wave has already been converted to electrical current. So the changing current causes the magnetic effects to change as well. So the change in magnitude of the current changes the strength of the magnetic field, and the change in direction changes the direction of the magnetic field as well. So when this happens on the coil becomes an electromagnet with changing magnetic fields and direction, so changing magnetic flux. This changing magnetic flux will interact with the permanent magnet. So for example, it could be attracted, could be repelled, could be attracted more strongly, attracted less, repelled more, repelled less. So these constant changes makes the cone move and produces sound waves. So that's how the magnetic effect of a current is used in a loudspeaker. Moving on to force on a current carrying conductor. So you need to be able to describe an experiment to show that a force acts on a current carrying conductor in a magnetic field. So when you place a conductor with current flowing through it in a magnetic field, this interaction causes a force that moves this conductor. So reversing the current reverses the direction in which the force moves, and changing the direction of the field also changes the direction in which the conductor moves. Changing the current or changing the direction of the field could change the direction of the force acting on the current carrying conductor. If you change both, then you have to check, is the force going to change or is it going to stay the same? How you do that is by using Fleming's left-hand rule. So Fleming's left-hand rule is related to number 2, which is where you need to recall and use the relative directions of force, magnetic field, and current. Now, because my video is in mirror mode, so I'm just going to use this hand. So this hand should look like your left hand. So remember that for Fleming's left-hand rule, the thumb represents the thrust or motion, also known as force. The index finger is the magnetic field, and the middle finger is current. So normally, how I remind my students to remember this, we use the feed my cat mnemonic. So feed my cat, FMC, force, magnet, current. If you have your own way to remember what each finger represents, please use that instead. Just use what you can remember easily. Now you also need to determine the direction of the force on beams of charged particles in a magnetic field. This is related to Unit 5, Nuclear Physics, where you need to be able to determine the direction of the deflection of alpha and beta particles in a magnetic field. You also use Fleming's left-hand rule in this case, where the charged particles are represented by the middle finger for current this time. Always remember that current is flowing from positive to negative. If the charged particle was negative, then you'd have the middle finger pointing the opposite direction instead, as if it's moving from negative to positive. So remember that. Now, for DC motors, you need to know that a current carrying coil in a magnetic field may experience a turning effect, and that the turning effect is increased by increasing the number of turns on the coil, the current, as well as the strength of the magnetic field. And how you remember this is that these are the factors which affect the force on the current carrying coil. You also need to be able to describe the operation of an electric motor, including the action of a split ring commutator and brushes. So what this means is that you need to be able to state the functions of the split ring commutator and carbon brush. And how you can write the functions is like this. For a split ring commutator, you can say that it changes the direction of the current in the armature or the coil every half cycle. So it's the current in the coil, because when the coil rotates, the right side goes to the left while the left side goes to the right, and the current within the coil would change because of that rotation. The current in the circuit remains the same. For the carbon brush, it is to maintain the connection of the current flow between the circuit and the armature or the coil. Now, for electromagnetic induction, you need to know that a conductor moving across a magnetic field or a changing magnetic field linking with a conductor can induce an EMF in the conductor. You also need to be able to describe an experiment to demonstrate electromagnetic induction. You must state the factors affecting the magnitude of an induced EMF, which are these: the strength of magnet, number of turns on the coil, the speed of movement or rotation, and presence of soft iron core. Now you also need to know that the direction of an induced EMF opposes the change causing it, and you must state and use the relative directions of force, field, and induced current. You have to be aware that there are two methods of electromagnetic induction. One way is to move a wire within the magnetic field between two permanent magnets, or you can move a bar magnet in and out of a solenoid connected to a circuit. When you have to determine the direction of the current flow in the wire moved across a magnetic field between two permanent magnets, you use Fleming's right-hand rule. So the fingers represent the same thing as with left-hand rule. You got again the force, magnet, current. So again, feed my cat or whatever method that works for you. So although it's written motion here, usually I call this force because it will be an easier distinction when we're feeding my cat. Essentially, left-hand or right-hand rule, force, magnet, current. The left hand is used when there's current provided because the current will make the wire move, whereas the right hand is used when you're inducing current. There's no power supply in the circuit. We use this to determine the direction of the induced current. To determine the direction of the current in the coil, this has actually been kind of taken out of syllabus because you would be using Lenz's law in this case. You don't have to really know the direction of current flowing in the coil. So just focus on the one for the wire moving across the magnetic field between two permanent magnets instead. From this, you need to know how an AC generator works. You need to be able to describe a simple form of AC generator using a rotating coil or rotating magnet and the use of the slip rings and brushes where needed. So similar to the DC motor, you need to be able to describe the functions of the slip rings and the carbon brush. So how you describe the function of a slip ring? It changes the direction of the current in the circuit every half cycle. So you can see now it's changing the direction of the circuit, not the ones in the coil. This is an AC generator, so remember, alternating current will change direction within the circuit. So the slip rings is used to change the direction of the current within the circuit. The carbon brush has the same functions as with the DC motor, which is just to maintain the connection of current flow between the circuit and the armature or the coil. In addition, you need to be able to sketch and interpret graphs of EMF against time for simple AC generators and relate the position of the generator coil to the peaks and troughs and zeros of the EMF. So remember that when the coil is at a vertical position like this, the value of the EMF or current within the circuit would be 0. When the coil is at a horizontal position like this, then the current would be maximum. At one part of the rotation, the maximum would be at the peak, and when it's done a half rotation, and then it's maximum on the other side, which is the trough. So basically remember this way: when it's vertical, 0, horizontal, maximum. If you've forgotten why, please watch my video about AC generators. So just a quick comparison between DC motor and AC generator, because I know a lot of students usually get very confused or they panic when it comes to motors and generators. So as a quick comparison, here's the function of the split ring commutator, function of the slip ring. The functions may look similar, but here's the difference. Both change direction of the current, but in the split ring commutator, it changes the current direction in the coil, because in the circuit, it remains the same. For AC generators, it changes the current direction in the circuit, because the circuit needs to change direction due to the need to generate AC current. Carbon brushes, whether it's in a DC motor or AC generator, the functions are the same. So in terms of how the AC generator is able to induce EMF or current, you need to describe electromagnetic induction. So you don't have to talk about, oh, you know what's going on in the slip rings and the circuit. That's normally not what they ask. You need to describe how the wires are able to induce current, which is basically explaining how when the wire cuts across the magnetic fields, this induces current. And the direction of the current is because the wire and the magnetic fields are right angles to each other, which causes the current to flow in the wire. Just a general reminder, I realize I haven't put it in the slides, but when you're asked to explain how the force direction or current direction is determined, please don't just mention, oh, the use of Fleming's left-hand rule or Fleming's right-hand rule, because that's the name of the rule. If they ask you for the name of the rule, that's what you write. But if you're asked to determine how the direction is obtained, you describe how all these components are right angles to one another. So that's what you should write in your answers. Now, for transformers, you need to be able to describe the construction of a simple transformer with a soft iron core as used for voltage transformations. So for transformers, you have to be aware that there are 3 main parts in a transformer. We have the soft iron core, which is usually in a square with a hole in it, and on both sides of this soft iron core there will be 2 coils. So we have a primary coil which is connected to the input circuit. The input circuit is the one with the AC power supply. And we have the secondary coil, which is connected to the output circuit, which is where we would normally connect the device that we want to operate. The secondary circuit does not have a power supply. Okay, let me move my face out of the way. The 3 main components of the simple transformer are the soft iron core, primary coil, and secondary coil. So that's what you need to know. Remember that transformers only work with AC power supplies. In your syllabus, you learn that they do not work with DC power supplies. So only AC. Just going to highlight that as a reminder. This is the symbol for a transformer. So you can see how the transformer reflects the actual construction. We have the primary coil, the secondary coil, and these lines represent the soft iron core. You must also know the terms primary, secondary, step up, and step down. So primary coil, secondary coil. Step up, step down, you should know that step up transformers will increase the voltage. So the secondary coil will have higher voltage than the primary, whereas step-down transformers are used to decrease the voltage. So the secondary coil will have less voltage than the primary coil. So as you can see from these diagrams, the number of loops on the coil will indicate whether the transformer is a step-up or step-down. For a step-up transformer, because it increases the voltage, the secondary coil will have more loops compared to the primary coil. Whereas for a step-down transformer, the secondary coil will have less loops on the coil compared to the primary coil. So how you remember all this is very logical. Just remember the transformer is used to transform the voltage, not the current, because current will be opposite. Higher voltage, lower current, lower voltage, higher current. So it can get very confusing. So focus on the transformation of voltage. Step up increases voltage, so more loops on the secondary coil. Step down decreases the voltage, therefore the number of loops on secondary will be lesser. You also need to be able to explain the principle of operation of a simple iron core transformer. So for this, I am taking an example of a past year question, which is quite a recent paper. It's the summer 2023 paper. So in this question, the students were asked to explain the principle of operation of a simple iron core transformer. So usually this question is worth 4 marks, and here are the 4 points you need to write. So let's refer to the mark scheme because that's basically what the paper is asking for, right? So you can write any 4, where you need to mention the alternating current in the primary coil. You need to mention that the current in the primary coil generates a changing magnetic field. So why alternating current? Because the changing alternating current will have a change in the magnetic field. So as the current increases, magnetic field strength increases. As the current changes direction, the magnetic field also changes direction. So the alternating current produces a changing magnetic field. What does the iron core do? It concentrates or transfers the magnetic field to the secondary coil. The secondary coil is within the alternating or changing magnetic field, or you can say the secondary coil cuts the magnetic field, which then induces an EMF. So how you remember this is basically it's a process. So start from the very beginning, talk about the process of how the transformer works. So you start from the primary coil into the iron core into the secondary coil. So that's how you can remember and explain the principle of operation of a simple iron core transformer. In addition, you also need to be able to recall and use the equation of Vp over Vs equals Np over Ns. This is quite simply a ratio formula which relates the voltage to the number of turns on the coil. So you can see how this ratio is reflecting the change in voltage. So a greater number of turns on the secondary will have a greater voltage, whereas a lower number of turns on the secondary will have a lower voltage. So just remember, the ratio of the voltage is equal to the ratio of the number of turns on the coils of a transformer. P and S of course refer to primary and secondary. So in addition, you also need to recall and use the equation for 100% efficiency in a transformer, and this is the formula. This formula is actually quite easy to remember because this is based on the P equals IV formula, or as I like to call it, the poison ivy formula. It's the electrical power formula where electrical power is calculated as the product of current and voltage, I times V. 100% efficiency just means that there is no loss in any energy or power. So the input power equals to the output power. So input power is on the primary, that's why IPVP, and the output power is on the secondary, which is simply ISVS. So that's how the IPVP equals ISVS formula is derived. It's actually derived from the electrical power formula. So in case you can't remember the formula, just remember the 100% efficiency just means the input power equals to the output power, and from there you should be able to derive the formula. Now you also need to know about electricity transmission for transformers, where you need to describe the use of transformers in high voltage transmission of electricity, as well as state the advantages of high voltage transmission. So what happens is when electricity is produced at a power station, whether it's hydroelectric or nuclear or coal powered, whatever, in order to transmit electricity to consumers, it has to go through a transmission grid. And when electricity is being transmitted, it has to be transmitted at high voltage. So that's why we need a step-up transformer to increase the voltage to a very high value. Typically, it's 400 kilovolts. and then when it reaches the consumers can't use voltage at such a high value. So we need a step down transformer to reduce the voltage so that the consumers can use the electricity accordingly. So normally it's stepped down a little bit first for factories like manufacturing and industrial users, so a little bit lower to 33 kilovolts. And then further step down for consumers like ourselves, whether residential, offices, or schools, usually about 230 or 240 volts. So these are the uses of transformers in the transmission of electricity. Step up transformer to increase the voltage for long distance transmission, and then step down to lower voltages for the uses of consumers. The reason why we use high voltage for transmission is because we need to reduce power loss. So the reason why high voltage transmission can reduce power loss is because if the electrical power is a fixed value from the power station, what happens when we increase the voltage is that the current will be reduced. So lower current can reduce power loss. Why? Because power loss is calculated from the P equals I squared R formula. So P is the power loss, I is the current that's flowing through the cable, and R is the resistance of the cable. So from this formula, as you can see, the lower the current, the lower the power loss. So that's why we use high voltage transmission. And that is the end of this unit. I hope you found this video to be educational and helpful. Do subscribe for more free physics lessons from your physics teacher, Miss Ho. If you'd like to help me keep making free educational video lessons and lab practicals, I do welcome some small contributions. You can go to coffee.com/physicsrocks. And if you'd like to get access to notes, quizzes, and syllabus from me, please visit my website at physicsrocks.com. All the best for your upcoming examinations and happy studying!